Hello everyone, welcome to my presentation. I am Seokhyun from University of Michigan. Today I'll be presenting federated multi-output Gaussian processes. This work is done with my advisor, Dr. Raed Kontar. Wireless communication and cloud technologies these days have increased connectivity across multiple correlated units. These multiple devices in many IoT systems are connected through central server on the cloud. This increased connectivity allows integrative analysis across multiple units. The key idea of this integrative analysis is to transfer knowledge across the units so that we can achieve better prediction or analysis over independent analysis. An MGP, also called multi-output Gaussian processes, is a popular tool for this integrative analysis. The idea of MGP is simply an extension of Gaussian process that has full covariance matrix that has covariances for both within and between units. For example, the covariance on the diagonal represents the covariance within units, and the covariance on the off-diagonal represents a covariance for between units. Based on this characteristic, MGP can transfer knowledge across the units based on this correlation. As a result, MGP has been a very popular tool for integrative analysis in many IoT systems. However, recent IoT system is experiencing a critical change. The edge computing power is tremendously increasing. The AI chips installed on Tesla EV is equivalent to the several hundred of MacBook Pros everyday use in the sense of computing power. This tremendous increase of the edge computing power has opened up new opportunity for decentralization of data analytics. In this work, we would like to introduce the decentralization of data analysis using multi-output Gaussian processes. Before diving into our proposed model, I would like to briefly introduce the standard approach for the decentralization while preserving the privacy, which is called federated analytics. Federated analytics starts with the global model in the central server. The central server broadcasts the global model to the units at the edge. Then the edge units locally update the model using local computing power and data sets. Then the locally updated models are sent back to the central server. The central server aggregates the local models, and the central server again broadcasts the global model to the edge, and the edge units locally update the received model. This procedure is repeated until some exit condition is met. If you use SGD for the local update and average for the aggregation in the central server, then it is fed average, which is well-known approach. However, our MGP is not amenable for this federated analytics framework. This is because federated analytics is based on empirical risk minimization. The key feature that empirical risk minimization enables FA is that the objective function of this framework is decomposable across units. However, because we adopt maximum log likelihood for MGP oftentimes, the objective function is log likelihood of Gaussian distribution. Therefore, it is not decomposable across units. As a result, we would like to introduce our approach that get around this issue. Basically, we exploit the natural hierarchy of IoT systems, which is hub and spoke structure. We place a common latent function that is shared through the central server across the units. Based on this common latent function, the units can share the commonality so that the knowledge is transferred through this common latent function. And we model G, the function G and F as Gaussian processes. However, the challenge is that the local datasets are needed to estimate the common latent function. To cope with this issue, we introduce pseudo-input approach. We basically introduce pseudo-inputs shared across units. The responses of these pseudo-inputs from the shared latent function will be marginalized out. This pseudo-input approach results in this MGP formulation as follows. In this MGP formulation, we found that the natural hierarchy of the IoT system. Basically, the output function f are independent given the shared latent function g. Specifically, this structure enjoys key advantages. First, we do not need to explicitly calculate cross-correlation when we model the correlation between two units. And also, we can achieve personalization because the f function can retain their unique characteristic while shared commonality across units, transferring knowledge. However, this does not tell us that it is amenable for federated analytics. Basically, the marginal log likelihood of this structure is still Gaussian distribution, which is not decomposable. Also, even after estimating the hyperparameters, the posterior distribution, which is a G given all the dataset locally stored, is not easy to derive because we do not have access to the local datasets in the federated setting. Therefore, we introduce federated inference using variational Bayesian approximation. Our idea is to place variational distribution Q of G that approximates the original posterior distribution G given all the datasets locally stored D1 to dm, and we minimize the KL divergence between these two distributions. And this is equivalent to maximizing an evidence lower bound, elbow, which is derived as follows. Interestingly here, the elbow is decomposable across units. It is more clear that elbow, if we express this elbow into the summation of the local risk, the decomposability is more clear. Furthermore, the elbow is composed of two parts. The first part is local model fit with the global parameter theta and the personalized parameter phi, and the second term is regularization using shared knowledge with the global parameter theta. This structure motivates us to develop federated analytics algorithm where edge units minimizes their own local risk, and also edge units collaboratively regularize the elbow by sharing the global parameter theta. As a result, we introduce our personalized federated inference algorithm. It starts with edge units that jointly optimize theta and the global parameter theta and personalized parameter phi using local computing power and data. Then, edge units send the global parameter theta to the central server. The central server then aggregates the collected theta, and then the central server again broadcasts the aggregate theta to edge devices. Then edge devices again jointly optimize theta and phi using local computing power. This procedure is repeated until some exit condition is met. So this procedure allows us to get the estimated hyperparameter in a federated fashion. Then we derive the predictive distribution. Another key advantage of our approach is the predictive distribution is derived at the edge. More specifically, the posterior distribution G given all the local data set D1 to Dm is replaced with the approximated distribution Q of G. And knowledge is shared across devices through QG because it is the distribution that is inferred by collaborative learning. Also, data sharing or centralized computation is not required in the calculation of this prediction. So in our simulation study, we generate data using the data generating model as presented, and we assume there are 5 units, and we assume also the federated setting where the units has computing power and the local data sets. And we remove some part of the data from a unit, and our goal is to extrapolate a curve for the missing part within federated analytics framework. And we compare our model with 3 baseline models. Our model is FedMGP average because we use averaging scheme for the aggregation in the central server. One baseline model is independent GP, and second baseline model is centralized MGP where all the data set is gathered into the central server and we use centralized data processing power and the database. And third one is the federated model. FedPoly is a 2-step federation and personalization approach based on polynomial regression. So in the first step of this baseline is to estimate the polynomial regression model by Fed average, and then we personalize it by solving this minimization problem based on the regularization. And here is the results. The left panels are representing the results of our proposed model, and the right panels is the results of independent GP. So here the results show that FedMGP, our proposed model, extrapolates the missing part by transferring knowledge from other units without sharing local data and using local computing power. And FedMGP is competitive to centralized MGP, which requires centralized computing power and dataset. FedMGP also outperforms FedPoly, showing better personalization achieved through our structure, which is better than 2-step approach. Also, FedMGP inherits benefits from MGP such as uncertainty quantification. So here the shaded area represents the uncertainty in prediction, and you can see that the uncertainty is well quantified. In the case study, we consider lithium-ion battery degradation. We use the COS battery dataset. There are 23 batteries, and the capacity decrease defines the degradation of these batteries. We randomly take 3 batteries for testing dataset, and we repeat this procedure for 10 times. And we remove some part of this test battery. So our goal is to predict the future evolution of degradation signal of the test battery at different degradation phases. For example, 30%, 5%, and 70% of the signaling is observed. So here is the result, and the left panel represents the result from our proposed model. And as you can see from this figure, our proposed model can extrapolate the degradation signal pretty well. It can predict the future evolution of the degradation signal pretty well. And it is competitive to the centralized MGP, while superior performance compared to the other independent or federated analytics techniques. Also, we observed that our proposed model can give better predictions as more observation is achieved. Finally, as a conclusion, we propose FedMGP, which is a framework where units collaboratively learn an MGP. And this, our proposed model, can transfer knowledge across units while exploiting edge computing and preserving privacy. FedMGP inherits significant advantages of MGP, such as uncertainty estimation and flexibility, as we've seen in both simulation and case studies. And we apply FedMGP to a real-world dataset on lithium-ion battery degradation, and we found that our proposed model is better than other baseline models. And many extensions can be proposed based on FedMGP, such as advanced schemes for central server aggregation can be proposed. Thank you for listening to my presentation. If you have any question, please let me know.